Welcome to the video lecture for Chapter 1, Section 7. This is for college algebra. My name is Jorge Gavilan. So in this, we have 5 objectives. We're going to go ahead and translate verbal descriptions into mathematical expressions. We're going to solve interest problems, mixture problems, uniform motion problems, and then constant rate job problems. So here's the modeling process. It starts with the real problem, verbal description, language of mathematics, a mathematical problem, and hopefully a solution to what we're presented with. So the first one is translate verbal descriptions into mathematical expressions. So for uniform motion, the average speed of an object equals the distance traveled divided by the time required. So the translation is that if r is the speed, d is the distance, and t is the time, then r is equal to d divided by t. For b, let x denote a number. The number 5 times as large as x is 5x. The number 3 less than x is x minus 3. The number that exceeds x by 4 is x plus 4, and the number that, when added to x, gives 5 is 5 minus x. So here are the steps when you solve a problem. So we've seen this before. I'm not going to read all of this to you guys. You guys can read that. And so the first thing is interest problems. So if a principal P dollars is borrowed for a period of T years at the per annum interest rate R expressed as a decimal, then the interest charge is equal to the principal times the rate times the time. So Candy has $7,000 to invest and wants an annual return of $2,800, which requires an overall rate of return of 4%. She can invest in a safe government-insured certificate of deposit, but it only pays 2%. To obtain the 4%, she agrees to invest some of her money in a non-insured corporate bonds paying 7%. How much should she place in each investment to achieve a goal? So the step 1, the question is asking for $2 amounts, the principal to invest in the corporate bonds and the principal to invest in the certificates of deposit. Let B represent the amount of dollars to be invested in bonds. Then 70,000 minus B is the amount that will be invested in the certificate. You see why? And then we're going to set up a table. And so bonds is B. Remember, we only have $70,000. So if I invest an amount B in bonds, I only have left the 70,000 minus whatever B is, what B is what's going to be left to invest in the CDs. So the bonds is the rate of 7%. The time is for 1 year. So the interest for the bonds is 0.07 B. The certificate is 70,000 minus B. So it's 2%, 0.02. So it's 0.02 times 70,000 minus B. So we have a total of, we want 4% rate, 70,000. So we want the 0.04 at times the 70,000 to be equal to the $2,800. Since the combined interest from the investment is equal to the total interest, we can set this up equal to the total amount that we want to get in return, which is the $2,800. So now the units are consistent. It's dollars on both sides. So we go ahead and combine. We multiply the distributive property. We combine like terms, and we get that B is equal to $28,000. So she should place $28,000 in the bonds, and in the difference of that, $42,000 in the certificate. So the interest on the bonds after 1 year at 7%, $28,000 would be $1,960. The interest on the certificate after 1 year at 2%, $42,000, is $840. And the total annual interest is $2,800, which is the required amount. Mixture problems. So blending coffees. The manager of a Starbucks store decides to experiment with a new blend of coffee. She will mix some B-grade Colombian coffee that sells for $5 per pound with some A-grade Arabica coffee that sells for $10 per pound to get 100 pounds of a new blend. Now, the selling price of the new blend is going to be $7 per pound, and there is to be no difference in revenue between selling the new blend and selling the other types. So how many pounds of the B-grade and how many pounds of the A-grade coffee are required? So we're going to let C represent the number of pounds on the B grade, and then 100 minus C will be equal to the number of pounds for the A grade coffee. And you can see figure 16. So $5 per pound, C pounds, $10 per pound, 100 minus the C pounds, and that's going to be equal to the $7 per pound, which is the 100 pounds that we want. So since there's no difference in revenue between selling A or B grade separately, the selling blend, we should have the revenue from B grade. So it's the price per pound of B grade times the pound of coffee for B grade plus the price per pound for the A grade, which is $10, times the pounds of A grade, which is 100 minus C, and the revenue from the blend, which is the $7 per pound times the 100 pounds. So now you can see here that we have 5c plus 10 times 100 minus c is equal to 700. Combining like terms, we end up with c is equal to 60. So the manager should blend 60 pounds of B grade with 40 pounds of A grade to get the desired blend. Now the 60 pounds of B grade will sell for $300, right? $5 times 60 pounds, and the 40 pounds of A grade will sell for $400. The total revenue is $700, which equals the revenue obtained from selling the blend as desired. The next one is uniform motion problems. So uniform motion formula: if an object moves an average speed rate r, the distance d covered in time t is given by d is equal to rt, or distance is equal to rate times time. Now Tanya, who's a long distance runner, runs an average speed of 8 miles per hour. 2 hours after Tanya leaves your house, you leave in your Honda and you follow the same route. If your average speed is 40 miles per hour, how long will it be before you catch up to Tanya? How far will each of you be from your home? So here we have the figure. So we use t to represent the time in hour that it takes the Honda to catch up to Tanya. Now, when this occurred, the total time elapsed for Tanya would be t plus 2 hours because she left 2 hours earlier. Now we're going to set up the table. Tanya runs at a rate of 8 miles per hour. Her time is t plus 2. The distance would be 8 times t plus 2. The Honda is going at 40 miles an hour. The time is t, and the distance will be 40t. So then the distance traveled is same for both. So 8 times 2 plus t is equal to 40t, which ends up being 32t is equal to 16, and t is equal to 1/2 hour. So it'll take the Honda about half an hour to catch up to Tanya, and each will have gone 20 miles. Now, in 2.5 hours, Tanya will have traveled a distance of 20 miles, and in half an hour, the Honda will travel a distance of 20 miles. Uniform motion for physics: a motorboat heads upstream at a distance of 20 miles on a river whose current is running at 3 miles per hour. The trip up and back takes 6 hours. Now, assuming that the motorboat maintained a constant speed relative to the water, what was the speed? So we're going to use r to represent the constant speed of the motorboat relative to the water. And then the true speed going upstream would be r minus 3 miles per hour. And the true speed going downstream would be r plus 3 miles per hour. Since distance is equal to rate times time, then time is equal to distance divided by rate, and we set up the table. So upstream, r minus 3, distance 24 miles, is 24 over r minus 3. Downstream, r plus 3, distance is the same. The time is 24 over the rate, which is r plus 3. So here it is, 24 miles, r minus 3, r plus 3 to return. And so we set this up because the total time back is 6 hours, right? Up and back is 6 hours. So we go ahead and combine the fraction. We get 48r over r squared minus 9 is equal to 6. Multiply both sides by r squared minus 9. Multiply out the 6, we get a quadratic, which is 6r squared minus 48r minus 54 is equal to 0. We're going to go ahead and divide by 6, so we just have a simpler quadratic to deal with. And we end up with r minus 9 and r plus 1. So we apply the zero product property, so we have r is equal to 9 or r is equal to -1. We're going to get rid of the -1 miles per hour. That doesn't make any sense, and conclude that the speed of the motorboat relative to the water was 9 miles per hour. So the next thing, we're going to solve constant rate job problems. So at 10 a.m., Danny's asked by his father to weed the garden. From past experience, Danny knows that this will take him 5 hours working alone. His older brother, Mike, when it's his turn to do his job, requires 6 hours. Since Mike wants to go fishing with Danny and has a reservation for 1 p.m., he agrees to help Danny. Assuming no gain or loss of efficiency, when will they finish the work if they work together? Can they make the golf date? So we're going to set up the table. In 1 hour, Danny does 1/5 of the job. And in 1 hour, Mike does 1/6 of the job. Let t be the time in hours that it takes them to do the job together. In 1 hour, then 1 over t of the job is completed. The reason is as follows. Part done by Danny in 1 hour plus the part done by Mike in 1 hour equals the part done together in 1 hour. So here we have the table set up. And so here's our equation. So 1 over 5 plus 1 over 6 is equal to 1 over t. We're going to combine the fractions. We end up with 11t is equal to 30, so t is equal to 30 over 11. And so working together, Mike and Danny can do the job in 30 over 11 hours, or about 2 hours and 44 minutes. Since they started at 10 o'clock, they're going to finish at 12:44 p.m., so they should make their golf date. And that's the end of 1.7.